Hello, everyone. Welcome to the second day of presentations. How is everyone doing?
Good, everyone good.
Awesome. So before we start, we're going to be going through 5 more presentations today. Very exciting projects today. I'm looking forward to all of them. The students are going to take about 20 minutes each, during which 15 minutes they're going to use for showing a demonstration video and their presentation, and we'll reserve 5 minutes for question answers after that, and anybody can ask the questions, including the guests. So before we start, I want to let the guests introduce themselves if they would like to, and just say your name and company or where you're from and your title for the sake of students. Please go ahead.
Yeah, hi. My name is Imran. I'm from California. I'm a consultant interested in robotics and look forward to attending this.
Thank you for joining, Imran. Anyone else who would like to introduce themselves? We have Dean Shamra joining us. Dean, you would like to say a few words?
This is Louis Shamra, Dean, School of Engineering, Computer Science, and I always look forward for these presentation. And I'm really proud of all the students and your project and what you do here at Auckland University. Congratulations on completing this project, and for the graduating seniors, we're very proud of you. I know it's been tough, but you guys persevered and you accomplished a lot of things this year. So congratulations, and I look forward for your presentation.
Thank you, Dean. And students, no pressure now. He's watching. Do a great job now. All right. Anybody else who would like to introduce themselves? Okay. Of course, we may have more guests joining us as we go, and please feel free to ask the questions after the presentation is done. So let's start. We're going to start with group number 6. Kyle, you're going to take it away. Please introduce yourselves first, say your name, and then share your screen, show your demo video and the presentation, and we'll have question answers after that. Go ahead, Kyle.
All right. Hi, everyone. We're group 6. My name is Kyle Allspa.
Hello, I'm Lucas Soroki.
Hello, everyone. I'm Malad Haddad.
Okay. Thanks for joining, guys. First, we're going to show our video of our project, and we hope you like it.
Hello, folks, and welcome to the Winter 2021 Robotics Championship. I'm your host, Kyle Allspa. We are coming to you live from the Robotics Lab at Auckland University, where we had the last match of the semifinal round. Let's get into it. The semifinal round is a puzzle round where the robot arm must solve the tricky triangle puzzle.
Kyle, you have to unmute your mic.
R700 is off to a great start, working through the top half of the puzzle first, make room for the bottom half. A brilliant strategy. Now keep in mind, folks, the KUKA absolutely needs to end up with 1 peg left on the board in order to beat out the FANUC arm and advance to the final round against ABB. The KUKA robot makes it look easy, though, just gripping away and putting those pegs down with authority. It doesn't fear a yellow painted robot arm. It doesn't need to say anything. Its moves are doing the talking. They're saying, you better be scared, FANUC, and I'll be seeing you in the finals, ABB. moving with precise, fluid motions. The KUKA is absolutely just crushing this semifinal round. It's saying, oh, this challenge? This is just another day in the office for me, Chief. The KUKA is just blowing away the competition, leaving everything in its dust. It has no remorse. It will not apologize to no one, man, nor robot. Group 6 is feeling confident their robot will end this round with the W and face their rival, ABB, in the final round. They have come a long way to get where they are at, so failure is not an option for them at this point. Coming down to the last few pegs of the puzzle, it is looking like a real nail-biter, folks. Will the KUKA get to the coveted one peg left, or will FANUC get a chance to force a tiebreaker between the two? Time will tell with these last few moves. Leaving nothing to chance, the KUKA makes it apparent that it knows what it is doing. This last jump means that the KUKA has just won the semifinal round, and boom goes the dynamite into the last slot. The peg goes. The crowd is cheering. The KUKA knocks down the pegs like dominoes. Well, that's it for us here today. Tune in tomorrow night to watch the Robotics Championship final to witness KUKA and ABB duke it out in a game of Rock'em Sock'em Robots to determine the winner of the 2021 RoboCup.
All right, so that was our video. I hope you enjoyed it. Now on to the presentation. All right, guys, as you saw in that brilliant sportscast of the Robotics Championship, we decided to tackle a tricky triangle puzzle. So a little introduction. If you're not familiar, the tricky triangle is a small handheld puzzle with the goal of jumping pegs over each other into empty slots and removing those jump pegs and ultimately ending up with one peg left. You may have seen this game from your grandparents, or maybe if you've ever been to Cracker Barrel, those games are always on the table. And so with that, the goal was, how do we get this into an application where a robot such as the KUKA could easily grip each peg and put them down. So we decided to, blow it up and to a decent sized board where the robot arm could easily maneuver through pieces and the gripper would not get into the way of each peg. And so with that, we obviously went to the hardware store, drilled up 15 holes as symmetrically as possible with given our tools. And you'll see later on how this rough iteration of this game board we had caused some issues with repeating the process once we got down with the programming. So with that, I'm going to turn it over to Lucas.
Yeah, so for programming the robot, we started the KUKA robot at the home position, and the movement was controlled by the teach pennant, and we moved the robot arm and the world frame from peg to peg, as you saw, and then every single one of those moves was a specific position, and we had to save it at every single point there. So like when it went over the piece, when it went down by the piece, when it grabbed the piece, lifted it up, over, down. It was pretty tedious, making sure we saved all those pieces. Next slide, please. Yeah, so some fine tuning and challenges we had. There was actually 250 lines of code after programming all the different moves. And the tool piece difficulty we had, you can see the tool piece on there holding one of the pegs. The tool piece is kind of like a horseshoe shape. And when you're grabbing it, it was kind of like grabbing with chopsticks at first, because on the lower part of the tool, there were some screws on the inside. And when you grab the piece, it would kind of rock back and forth. It wouldn't necessarily always grab the best spot inside of there. So After trying it out a couple times, saving all the code, we finally decided that it'd be better off to, as you can see in that picture, we use the upper half of the tool piece, which was squared off, and that made it uniform. So every single time we would go over, grab the piece, it would make sure we grab it from the same spot every single time. Some of the board tolerances. Kyle's a great woods craftsman, but it's not perfect doing it by hand for every single one of those pieces. He thought about even getting a drill from Harbor Freight or something, but decided not to. We had to tape the board down to prevent it from moving around when we were grabbing each of the pieces. And quite a bit of time was needed to complete the puzzle. Next slide, please. Yeah, so for executing the program, there are many different ways to solve the tricky triangle game, but we used the most popular solution, which involved the least amount of steps. And so, for example, like we numbered each of the pieces and said like piece 1, jump over piece 3, take out piece 2. And throughout that whole process, yeah, we had to save every single one of those spots. And like in the real world, there's always difficulties. You just gotta go with them, go with the flow, adjust, react, and be able to solve the problem at hand. And for the KUKA robot, we all enjoyed working on the KUKA robot. It's very straightforward, and it was nice with the XYZ, be able to go from left, right, front, back within each of the frames, and going from the forward kinematics, inverse kinematics, grabbing each of the pieces and stacking them all up in line there so we could finally knock them all down. I'm going to kick it over to Malad.
Hello, everyone. So I'm going to talk about improving the application. So after finishing the project, we went back and talked about what we could have revised about the building process. And the problem was, as we mentioned, the board itself. It was not built with a good tolerance. And if we have more time, we could have built it with better tolerance and reduce the difficulty of movement to set up the pig on the right place. Also, the speed of the robot was one of the problems that we had. If the speed of the robot on the manual control was as fast as how it was on the auto control, then that will ease up the movement of the robot to solve the game. While we're programming, we use the manual control. And while we tried the whole process, we used the auto and it was completely different speed. Like when it was 100 speed, it was still slow when we're trying to control it on the manual, but when we switched it to auto mode, that made it way easier and fast to solve the game. Another point is the point of view. If there was an option of adding a camera on the top of the gripper, or if it was like camera on the area of the work, that would ease up the vision of the movement, because our problem was like the hole was so small. And as we mentioned, we had a problem to fit them together. So while the robot was moving, we had a problem to see where is the gripper moving and if it's on the right position and the right place to set up the pig on the hull. And that would be solved if we had a camera on the top of the gripper on top of the area work. And that was the problem that we had, and we discussed that it could have improved the application if we had it resolved. Next slide, please. Okay, at the conclusion, at the way that we pursued the program, it gave us a better understanding and good knowledge of how robot work. During the process time was passed through some challenges as usual, and but at the end the application was accomplished. The project was a great observation of how would approach a program using robot in real world situation. Overall, it was a great opportunity and a nice experience to be able to create an application from scratch and use a robot to solve it. Like when we start, we just had an idea, we built it up, we went to lab, tried many times, had some difficulties, and we ended up finishing the project with a really good experience and nice learn. And that gave us a really good vision of the robot that we can use it in any application that we can think of and resolve it if it's small or big. Next slide, please. I hope you guys enjoyed it. And any question or comment?
Great job, Group 6. Good demo, good presentation. Kyle, can you unshare your screen? All right, so we are open for questions for Group 6. Anybody has a question for them?
I was just gonna say, I feel like I've only solved the tricky triangle maybe once or twice in my life.
Yeah, you know, it's probably going to be like 6 months from now. I'll probably walk into Cracker Barrel and they'll be like, I know how to solve this, and I won't solve it. I'll score
By the way,
ignoramus.
Same here. Sorry to interrupt. I've never solved it. And when we started the project, I was like, Kyle, you have to teach me how to solve it to understand what's going on. And he did it many times in front of me to be able to vision like what we're trying to do, because I've never played it. So it was hard at the beginning to get the point of the project.
So
Awesome.
I'm assuming there is only a limited ways to solve it, right?
No, I would say there's few ways, but because obviously you have to start with one hole open. So I mean, that's at least 3 different ways if you did the same pattern.
Mhm.
But yeah, I don't know. I mean, it's I'm sure there's some sort of algorithm that someone came up with. Maybe some mathematicians went to Cracker Barrel one day and were like, huh, let's figure this out. Let's get down to the brass tacks.
I guess the starting position is important. You know, where is that hole which you're trying to solve, right?
Right.
Okay. Any
I
other
was telling them we
questions?
should go to Cracker Barrel and like sell the video to them for an advertisement.
Okay, so you guys got into issues with the tool, as you now understand that the design of the tool, what part you're trying to pick up becomes extremely important, not only to just pick up the part, but the accuracy of the whole application. So I'm glad that you learned it, well, maybe the hard way, how to solve that. And one way you solve this by increasing the size of the board. What would you do if you had to actually play that small board with that robot? What kind of tool would you design for that? How would you pick up that little peg?
Obviously, none of us have 3D printers, but I think we would have to, you know, start getting into some small parts just to, you know, pick it up. We could, yeah, I mean, it's really, you really need to grip it, because you can't just, if we had something, one of the videos you showed us from 2018, someone was picking up little bowling ball pins with a little tool. You know, that's an option we could have done, but you know, like I said, they start, you know, getting all wacky when you pick them up, and you need to have them, you know, gripped and precise before we could move them and put them in slots.
So one common way in industry is to use suction. So if you have suction, it is a very reliable grip, and it'll just pick it straight up and straight down. So if you can design a tool with a small suction where it just conforms to the peg properly, and if you can reliably pick up using that, it can go in very tiny spaces to do. So what I'm saying is there are many options. And like I said, tool designing is a whole engineering on its own, you know, how you design an effective tool. Another thing is that if you had designed the board in CAD, and could you have used the CAD data for your programming, the robot?
Certainly. I think, you know, I mean, obviously CNC exists, and obviously if we were more advanced with programming the robot, I'm sure it takes input from outside data. It could definitely, that's one of the things Lucas mentioned or asked the TA, can we program certain spots? That way, you know, we're not constantly readjusting and adjusting every time we run through it. So yeah, for sure.
Yeah, I like numbered all the pieces in there, whatever, 15 pieces. And I was like, okay, if we, like, I remember like with the tool frame, we can find where that piece is at. And then we could like grab each one of those pieces. If we had the coordinates of every single one of those pieces, we could essentially just input the coordinates into the computer program and make it a lot easier.
Exactly. So a lot of time the offline programming is done that way, that your model is in CAD and you program using the coordinates in the CAD data. But you wanna do it relative to the part. Because if the part is positioned, the whole program moves with the part that way. And you don't have to teach the points. You just have to teach the frame where the part is and align it with the robot. So those are a few things where when you do practical applications, and this is why, I asked you to do some hands-on, because this is where you learn that when you're trying to do those stuff and you have to redo stuff, how much effort it takes to redo stuff, or what's the way shortcuts to avoid, reteaching robots and stuff. Excellent. Last question. Anybody else has question? I do have a few questions there, because this is useful to teach you, some of the practical aspects of doing application. So one of the things you guys mentioned was use of vision to insert, for accurately inserting. Do you think vision will help in accurately inserting a peg in a hole?
I think yes, of course
Yeah.
that would help, because like I was imagining when we work on the robot, if we have a small camera connected to the gripper or like at the area, and like we can see the movement on the screen of the touch pan, that would help a lot. Because like Kyle was trying to move the robot, and me and Lucas were trying to see if it's going to the right place, was really difficult. So we were trying to see from the side, top, and that was like really difficult to decide if that is the end position of the point. So I think if we use vision to like be able to actually put the picks on the right place. Also, like a camera with sensor, that would have made it even easier. Like was like if it's close to the place, it gives us a green light that it's perfect on the right place and all that. That would improve a lot the project and the actual robot itself.
Okay,
It
so
reminded me of,
so vision can help you locate where the hole is exactly where you're trying to insert. But if it's very, very tight tolerances, what else could help? I mean, think about it. If you are trying to insert a peg in a very, very tight hole, like there is hardly any tolerances. If a human is doing it, how does it do it? What does it use besides vision? Well, vision, you put the peg right at the hole, but as you are making the actual insertion of the peg in the hole, what other senses do you use?
Pressure.
Yes. So you need some force feedback. So you will have, and a lot of times in industry, they use the sort of a jiggle motion to kind of align. And then as soon as you see movement going in the peg, it's going in. So yeah, force feedback. So remember in our last lecture, we talked about that. This is the type of application where you would use this kind of, if your tolerances are extremely tight. Okay. Anyway, any last questions for group 6? All right. Great job, guys. Awesome. Okay, we're going to move on to group number 7, and they're doing robosurgery. So group 7, introduce yourself, then share your screen, show your demo and the presentation. So
Yep, just a second on it. Yep. So hello everyone, we are group 7. Our project is called Robosurgery. My name is Shi Yu Yang.
I am Jacob Peterson.
I'm Walid Alamar.
And I am Hadi Najjar. So the main purpose actually of this project is we wanted to prove once again that robots are much, much more precise than humans are. I know you all trust driving a car or whatever, but how about thinking about someone other than a human being giving you stitches, or a robot digging in your mouth, filling a tooth cavity? I know it might not sound very pleasant, but we might change your mind after showing you this project, hopefully. So we decided to show you one simple example, and we're gonna tell you what we will be mimicking in a second. So one of the main reasons we actually thought of this project is because we realized that medical mistakes are actually the third leading cause of death in the United States. And of course, part of these deaths is due to imprecise usage of medical equipment by surgeons while they're doing the surgery. So we wanted to talk about this before we show you the video demo, just so you can relate to what we're talking about. The project we're doing kind of mimics what's called an angiogram. And an angiogram is pretty much a catheter that's being inserted into the blood vessels, right? And mainly the veins. And it goes all the way to a certain part of the area. It's very common in the heart. So this type of angiogram, there's a catheter that goes in and it has to navigate through the blood vessels all the way to a certain place. And then the surgeon has to pull it back out. If you look at this simple figure, you can see how long the actual path could actually be. And when working on a smaller scale, like the micro or the nano, this definitely becomes much, much harder for it to be precise. So you can imagine how precise someone has to be and how steady the catheter has to be going in and out. So like we said, we decided to mimic this in a way. So we had two main parts of this robot. We have a tool that has kind of a spherical and a linear shape that's going to be guided through a ring that's steady in its place. And at the end of it, we decided to put some dominoes and knock it just to prove our success, I guess. So we're going to go ahead and show you our demo and to show you how this robot is going to work.
All right, so that was our video. I'm just going to talk to you guys a little bit about the design, kind of what went into the background of getting this to happen. You can see in the picture on top, there's our tool on the left and the target on the right. The tool is basically a piece of wire bent with a spiral and a zigzag, which we had to guide through the ring. And you can see in the picture on the bottom that the tool is mounted at a 90-degree angle to the last joint of the robot. It took a little bit of playing around to figure out how to hold it so that we would have the most flexibility so that we could avoid the singularities while guiding the tool through the target. Also, if you notice in the picture on the bottom, the red wire running from the tool down to the base of the robot, the red wire is connected to an Arduino, which is hooked up to the buzzer to verify that we don't bump the tool to the ring as we go through. Also, you can notice how the tool has a plastic block to insulate it from the robot. So here's just kind of a flow chart. You can go to the next slide. Here's just kind of a flow chart of basically what our program does. We start in the home position, and then we bump the tool to the target to make sure the alarm is working. as we start the procedure, we use circular moves to guide the wire through the curved sections. And then we use straight moves or linear moves to guide the straight sections through the ring. And once we're all the way through, we can tip over the dominoes. Next slide. So how we programmed this, basically we just had to manually drive this tool through the ring with the teach pendant and record lots of points, as you can imagine. Like I already mentioned, we used linear moves for the straight sections and circular moves while going from point to point, changing orientation through the spiral. If you look at the picture on the bottom left, that's just us in the lab trying to figure out how to do it. The picture on the bottom right, you can see the red arc at the tip of the tool. Basically, that's the path that we're programming the tip of the tool to follow as we change orientation at the corner that's inside of the hoop.
All right, so as the result, these are all the codes that we pulled out from the robot or the teach pendant. So the first slide is pretty generic. This is just when we were doing the test function of the alarm system or the buzzer system. And the next will be the code that we are going through the spiral session. As you can see, most of it is we are using the circular move. And next one will be the zigzag section. We pretty much use a combination. You know, we are rotating linear move to circular move and then circular back to linear, stuff like that. And these are showing all the positions that we programmed. We skip a little bit, but you can see from point 1 to all the way to point 59, we have so many points programmed. So as the observation, I believe the demonstration video pretty much shows that the robot motion are very smooth, precise, and stable, as we do hope this can be a real medical application. And setting multiple points in their circular motion, that works just great for nonlinear path scenarios, like what we did for the spiral. And also changing the tooltip points, that would help the robot moves more precisely around the specific center. That's actually what we did for the zigzag session. We just end up rotating that around the where it turns. And also the last one will be due to the robot joint limits and singularity, the robot initial position of each joint. It must be carefully considered during the design phase just to maximize the running distance along all directions and rotating angle of each joint. All right, I'm gonna pass it to Valid.
As a conclusion, we can say that we were able to achieve the main purpose, which is guide the tool through the ring and knock down the dominoes chain. The project shows high precision and accuracy when entering the wire ring. This project helped us to apply the concepts that we used during the semester and we learned during the semester, and gave us the opportunity to get familiar with the use of the teach pendant. The project emphasized the idea that robots can be easily programmed by saving the points of the desired path to automate the process. Next slide, please. Some of the lessons that we learned and challenges we overcome during the projects. Using robots for complicated tasks is a way to eliminate the human errors and mistakes that can occur. Using robots can accomplish many tasks with a very short time frame. Finally, a lot of experience were gained during this project, and it can be used in many industries such as medical field, automotive like welding and assembly, human collaboration for assembly, etc. Thank you guys for watching, and any questions?
Good job, Group 7. Good demo, good presentation. All right. We're going to open up for question. Can you unshare the screen to you?
Yep.
Thank you. All right, let's open up for questions. Anybody?
Anyone wants an angiogram?
Okay, well, let me ask you a question. So I was wondering what kind of moves you did. I think you are the first group to do circular moves using a robot. So kudos to you for doing that. Now, for the sake of everyone here, you want to explain how does the circular move work on FANUC robot? You know, what points does it need for it to move in a circular arc?
Yeah, I can explain that.
Mhm.
Basically, imagine my arm is the robot, okay? And my finger is the tip of the tool. I can use a linear or a joint move to move the tip to a specific point. This will be the start point of the arc or the circular move. So then I can tell it that I want to do a circular move. I can teach it a second point, maybe up here, and a third point down here. So then when I execute the program, it will follow an arc through those points. Is that clear?
Yeah, so it's a 3-point circular arc. So
I'd also like to add that if I teach it a point here and I teach it the second point at a weird orientation and the third point at another orientation, it will still move the tip along that arc as it changes orientation. It's kind of complicated to imagine, but it can do that.
So essentially, the position follows the circular arc. The orientation has a smooth change going from between the 3 points. Is that what?
Yes, exactly.
So yeah, so this is a very, very interesting move, especially for your application that it worked very well.
Yeah.
Awesome.
We did a lot of playing around to try to figure out what would work good, and that seemed to do a good job.
So if this was a real medical application, your data is coming from the patient, maybe from CT scan or something, where you have to traverse this catheter, right? Catheter. So how would you generate points for your robot based on the information which is coming from scans? Any ideas? What would be the process there?
Oh, I knew it's gonna be a question. Maybe I'll start on this one, and everybody else, please help me after this. So
Okay.
I thought about it.
Yeah.
One thing we could do is once we have the CT scan, we can use the CAD model kind of thing just to get the points. Like I showed earlier, we have totally of 59 points. We use all the special specific points of the CAD model to replace those 59 points. Also, because this is about life, human life. So nowadays there are so many technologies, like we can even print out 3D model just based on the patient, specific scenario. So we can pretty much teach the robot just like visualize by the 3D printer, print out the 3D model and teach it and kind of test it and then use it on the real patient. And also I was thinking maybe build a tool frame, something like that. Just get a base frame as we practice and then swap out to the real patient.
All right, excellent. Now you have a frame on the patient somewhere, huh?
I was about to say,
we have to.
But we're probably going to use many, many more points. I mean, you're probably going to use a couple thousand points at least to be much, much more precise. You don't want to open up someone while inserting catheter.
I don't know if there is a robot which exists which does this thing yet, but do you think this is an open-ended application, meaning you teach it and it does it, or is it you gotta have a camera at the end of that catheter which is giving you live feedback and you adjust as you go through the narrow openings and all? So it might be that you gotta tweak your motion as you go through the body itself. So I don't know if I can imagine it as something which was taught and it just does it without any feedback coming back from the actual patient. So it's a mix of both, that you teach a certain motion for it to go through and it's adjusting itself as it finds going through the process itself. So it's an interesting application. Even the Da Vinci robots which operate are not autonomous. There is a surgeon behind it who's actually controlling it, all the operations with it. So we are waiting for autonomous surgeons, robots which do that. There may be some coming which do, you know, operations like stitching, things like that, which are kind of repetitive tasks, and you can program robots to actually just do, when a surgeon is done with his work, they just stitch up the patient and do a great job doing that. So there are things coming up like that. So it's very interesting application. You mentioned singularities. Now, what would be a good way to avoid that for this particular type of application?
Oh, we are so prepared for that. So Jacob, do you want to talk about it a little bit? And I'll probably do it after you.
Yeah, I'll do what I can. It seems like you'd have to have a robot that was designed for a very specific application. So if it's designed for a specific application, you can design it with basically joint limits that fit what you need it to do. That's kind of a tough question though.
So it's a specially designed robot, you're saying?
It seems like for a task like this, that would probably be a
what
way
would
to
be
do
a
it.
simpler way using existing robots? What would be a good robot to avoid singularities? We did talk about that.
If it had redundant joints,
There
meaning
you go.
like, yeah.
Yeah, so the newer robots, collaborative robots and others, they are 7 degrees of freedom.
Mhm.
And if you run into singularity, you just change the arm configuration without changing the tooltip position, and you could avoid singularity and keep on moving. So yeah, so there may be robots which are more suitable for this kind of task. All right. Any last questions for group 7? Come on, guys. Nobody has a question? All right.
I just thought it was cool when I saw it in the lab last week.
It is cool. It's a cool app. All right, guys. Great job.
Thank you, everybody.
Thank you.
Okay, moving on. Group number 8 is going to show us Grandmaster Robot. So group number 8, introduce yourself, show the video and the presentation. Go ahead.
Hello, my name is Haralam Chilipiri.
And my name is Rami Suleiman.
My name is Zachary Page.
I'm Santiago.
We're going to present the Grandmaster robot for you. We're group 8. First of all, we would like to thank you everyone for coming. I don't like to waste more time, and I want to start with a quick video we have. It's a chess game between the X arm and the Li arm. We're going to talk a little bit more about the movements of the chess game in the upcoming slides. So that was a fun game, not for the Li arm robot below. Okay, so we all have seen that the use of robots is rapidly growing across many industries for a variety of applications. For this project, we were able to use not 1 but 2 robots. The X-arm was provided by Auckland University Resources with the help of Professor Mirza. So I'd like to thank everyone who was part of that. And our group also provided the Lee arm. Firstly, we were going to use only one, the X arm, and me playing against it, but then decided to make it more enjoyable for the robot because it was too easy playing against me. So we added another one, but the X arm still won. So a little bit about the chess game. The first movement, it's basically one of the most common chess games moves. The pawn moves straight up 2 squares. The Lee arm follows it. Then the bishop goes diagonal. But then we wanted to make it a little bit more difficult for us. And since the knight is the only one that jumps across the other chess pieces, we would like to see how the robot actually reacts to that. How can it get the knight right there where there are so many other chess pieces and actually move it to another place without throwing anything down. Then the queen moves diagonal. The Lee arm does just a simple move here, and that's when the queen gets the pawn here, and it's a checkmate. That's when the X arm went crazy. Then Santiago will talk a little bit about programming.
All right, so to program the robotic arms, we use the software that came with these robots. And then to program each robotic arm, we move the arms to the desired points and then recorded the servo angles in the software. And then we just ran the sequence, making sure to include all the delays necessary for each arm to make each chess move. And in total, we recorded about 60 different points for each robotic arm. And then the workspace for these robots was a 9x9-inch chessboard. Originally, we wanted to use a bigger board, but due to the size of the robots, we had to stick with a smaller board, which made it a bit challenging when trying to pick up the pieces without knocking over the other pieces in the board. And then we didn't make any modifications to the end effector tool. We thought we might need to add some like half cylinders to the grippers, but the gripper in the robot was sufficient to pick up all the pieces. And I'll hand it over to Rami to talk about the challenges.
Thank you, Santiago. So of course, with every great project, there are some challenges that come along. Some of the challenges that we encountered during this project is the tabletop robot was not built for precisions. And for us, we're handling very small pieces that we're trying to pick it up and place it in a specific spot. So it wasn't precise enough to be able to pick it up every single time from the same spot. Another challenge was hardware, whereas it kept on getting loose after running like trials on it. It's just from the vibration, and then from the trials, it was just becoming loose. And it was difficult to repeat a step in the same position. And then that's because of, one, that robot is not very precise, and then also the hardware kept on coming loose, which made the gap for tolerance error a lot bigger, and it was like shaking more, and there was more play in the arm. Another challenge is the size of the robot. We weren't able to reach all the way across the board without knocking down some of the pieces in the front. The improvements that we came up with is to have a better hardware to stay secure. For example, like adding washers or lock washers to the screws or nuts. So with the kits, I only just came in with a screw and nut. And then, of course, as I mentioned before, with the vibration in the trials, it kept on coming loose. Another thing that we can improve on that is adding Loctite to secure the servo, and stay secure to the brackets, along with the washers. And then, if we take it up a notch a little bit, we can also add like torque specs on each screw on there. Also adding a vision system with more time given, just to enhance the project. Also, we could add sensor to chessboards. We can add on each piece. We can have a sensor on each spot. We can have another sensor so we can detect where that piece is. And then for later projects, we can have the arm or the robot decide what move it needs to make. And then definitely better precise the tabletop robot. That would be nice. And then I'll kick it off to Zach. Who'll go over the conclusion.
So for the conclusion, I'm going to talk a little bit about applications, hardware, software, and artificial intelligence. These robotic arms are best suited for simpler applications like the one in our project. Luckily for us, Haralam is a professional chess player in Albania, so he was able to offer an educated opinion on this matter. He stated that when competing in chess, it is preferable to play with a real board and pieces rather than on a computer screen. This allows you to visualize the workspace much better than you could on a monitor, resulting in an improved playing experience. So when playing against someone else remotely, the robot could make their moves for them. For the hardware, we already discussed how there were some issues with accuracy and loosening bolts and nuts, but we were able to overcome these difficulties and still achieve the outcome we desired. The software we used to program the robotic arms was adequate for this application, but using Python would have been easier and more robust. Finally, the main improvement we would like to accomplish would be adding machine vision and artificial intelligence so that anyone could play a simulated chess match in real life against a rage-quitting robot. Thank you all for listening, and we will now be accepting questions.
Oh, I was muted. Sorry. I said great job, group number 8. Good.
I was like, no questions.
Okay, we're open for questions. Any questions? No, help
I
your.
guess I have a question.
Go ahead.
So you said that the robot was not super precise because of just the build quality. Do you know if turning down the speed would have possibly helped with the precision? Because I noticed when it was moving fast, it would kind of jerk every single time it stopped, and maybe that was contributing to the lack of precision.
Actually, can I answer that question? We tried adding more points to the arm, but that just makes the arm go crazy, and it was like so slow. It was like adding every point like this. That actually helped a little bit. So what we try to do when the arm makes that big movement, since the bolts are loose, then you go more forward than you actually want to do, than what you actually program it in the beginning. So in the beginning, we stopped a little bit before the actual point that we wanted to stop. And then we made that small movement in the end. So it doesn't get that much error right there. But adding too many points to that was not working for that. I don't know why I thought about that. I thought, oh, let's go, guys. Just keep pressing that button and we say all these points, but it didn't work.
What type of teaching method did you use for programming this robot?
So we had two, the X arm and the Li arm. In the beginning, we tried to implement the coordinates of both of them, but it was since the chess pieces were too small, we had a big error, and we couldn't make a chessboard bigger since the arm was small, and the grip was moving more than we wanted to actually move. We just made a self-memorizing for the robot.
No, I mean like actually controlling the robot. Were you using the joystick control or the application, the smartphone application?
We use for the X-arm was actually easier because it had we actually moved it by hand, but for the Li arm we had to use the application from the laptop. So we kind of used two different programming. For the X-arm, we just moved it. But for the Lee arm, Santiago actually can talk a little bit more about that.
Was it what type of moves were between the point? Joint moves or linear moves?
It was just moving the robot to the point that we wanted it at, and then just moving it to the next point, and then just recording each point in between each move.
No, I meant
the linear moves.
The motion between the points was linear or joint moves?
Linear.
Linear. Okay, so well, you mentioned bolts coming loose, and did you guys assemble it properly, first of all?
Yes.
You didn't tighten the screws enough?
We did, but for some reason the X arm didn't have the washers. So the bolts were just getting loose for us. We tried to just screw them in again. After 10 tries, maybe it gets loose again, and you just have to screw them again.
So here is a question for you. What kind of robot motion will make your bolts loose? And we talked about that in one of the lectures, that there is the motion between points. So a type of motion is not good for the hardware of the robot, and it can cause bolts to loosen up and other issues, hardware issues. You guys remember that? Any one of you?
Linear motion.
Well, what kind of motion profile?
Any like rapid, sudden accelerations, more or less.
Exactly. If your acceleration is discontinuous, so you have jerk. So the jerk, the start and stop of the motion is really hard on the mechanism, robot mechanism. So when we design our moves, the profile for the motion, normally we try to have a smooth acceleration, right? So if you had a chance to do work with Python, let's say Python interface with this robot, and you could actually do the motion profile, it'll be much better that the start and stop is controlled, and it's not going to loosen your bolts that much. I mean, if the bolts are reasonably tight, then it's not going to make it, hard on you to have this issue. So that's one thing. In industrial robots, the real robots, this is one of the big reasons they have the motion profile for that. Not only because it's smooth going between the points, but it's not hard on the robot gearbox and other mechanism, because that's important. Here you're loosening the bolt. There, after so many months of operation, you're breaking gearboxes, and that's a much more expensive thing to repair. So it's very important that these robots, which have to work day in, day out, for months and years, that they don't experience these problems. So motion profiling is a very important thing for these robots.
That's a good point.
Go
I was
ahead.
just say that's a good point, Professor. The more advanced robots will help you control that. There's algorithms to kind of keep you in a box, if you will, when you're programming, but at the same time, they also let you do a lot of crazy stuff. So if you program it to be jerky, it will be jerky. Now, if you tell it to do linear movements, it'll adjust itself with the weight and then understand how fast you want to go somewhere. But you do have to be careful in programming.
That's right. Thank you. Any other questions for this group? By the way, yeah, go ahead.
So in the hardware, instead of using washers and all, why don't they use lock nuts? Because lock nuts basically do provide you a lot of security over loosening even with vibration.
Yeah, I do agree. Yeah, I do. I have worked with lock nuts. The only problem with lock nuts, if you want to assemble and disassemble the robot, technically the lock nut should be used once. But yes, I do agree. You can use a lock nut. That would be a good idea.
Did the kit come with lock nuts or not?
No.
Okay, we need better robots.
Yeah.
Or just better hardware. The robot is good. The servos are good, and I wish also the servos were made out of metal gearboxes, because over time, as we're gonna use it, that air in each gear is gonna get bigger and bigger, and then it's just gonna become loose, and it's not gonna be precise over time.
Agreed. I mean, you guys are the guinea pigs. We just got this at the last minute. The real robots are fairly expensive. We couldn't get 10 of those for each of you.
Yeah.
So,
No,
we are always on a lookout for a good robot kit for educational use, which is reasonably priced, so we can get quantities of that and loan it out to students. I mean, now you can see the actual industrial robot, the quality of that. Why is it so costly? It's the precision and the hardware which goes into it. The gearboxes, the motors, everything, and that makes it an expensive piece of machinery.
100% agree. And like we definitely put that robot to test. And we did we gave it a fair chance, and then we reviewed it really good.
All right.
I would like to say I'm sorry if I missed anything because I got disconnected, but I would like to say that when I was looking at the industrial robots, I was like, I wish we were using that right now.
Yes.
Just because it was so precise.
Yeah.
Yep. Agreed. Well, we were talking about your grade while you were gone, so you didn't miss much.
Did I pass?
I think you did. So by the way, guys, when you're showing the demo videos, I know it's coming out a little bit choppy and the sound. All of this will be available on YouTube. So go on that link which I have already sent, and these videos will be there for you guys to watch it in full glory. Okay. All right. Any last questions for Group 8?
Were the robots talking to each other, or you just started the programs at the same time?
Good question.
We just started the program at the same time.
That's fine.
It would be better if we communicated, right?
Yes, but if we actually had artificial intelligence, then it was going to be a tie all the time. Because they were going to be smart both.
Yeah. Well, then you have to sense other robot has moved, so it's your turn now. And you have to hit the timer also, right?
Yeah.
Okay. Good job, Group 8.
Thank you. And I do want to thank you, Professor, and all the guest people that showed up today. Thank you.
Thank you. All right, we're going to move on to group number 9. Oh, we have a Swedish IKEA robot coming up. So group 9, please introduce yourself and then share your screen, demo, and presentation. Go ahead.
Okay. Good evening, ladies and gentlemen. Group 9 coming at you with our amazing, not IKEA knockoff furniture builder for our final project. I'm John.
I'm Jared.
Hi, I'm Desmond.
Can't hear you, Vic.
Can't hear you, Vic.
Oh, can you hear me now?
Yep.
All right,
Yes.
yeah, I'm Victor.
And without further ado, here is our video introduction. Let me share the screen. All right, can everyone see it? Yes, okay.
Good pickup. Two in a row. Perfect!
No! God, please, no! No!
Well, I certainly hope everyone enjoyed that. Especially, I especially hope Professor Mirza enjoyed that last bit. Well, going off our agenda here, we will be having Jared taking charge with the design, and with yours truly with the revisions. Desmond backing us up with the execution, and Victor finishing us off with the application. Take it away, Jared.
All right, thanks, John. When it comes to designing any of these projects, obviously, first of all, you need to clearly establish what your problem that you're trying to solve is. In this case, we wanted to take some simple modular parts and construct them into sort of like minimalist furniture, kind of in the vein of what you would find in like an IKEA or some other sort of simple furniture assembly. And when we were choosing our robot that we wanted to use, we were looking for the robot with seemingly the biggest workspace, and in this case, the KUKA robot that was available to us seemed to have the largest workspace so that we could really assemble a large piece of furniture. And yep, it's good. The constraints obviously have to come now that we've established our problem, and in this case, we have problem-based constraints, which were kind of constraints that we invented ourselves, and robot-based constraints, which are for the most part out of our control. And when it comes to problem-based constraints, there's quite a few of them, but just quickly, we need to have quick assembly and modular parts because that's kind of like just the general goal that we were going for there, just to replicate IKEA type furniture. We needed rigid connection because the furniture can't fall apart, obviously, but we also needed to be able to disassemble the pieces because they're test pieces and we're going to have to assemble and disassemble and several times. And then finally, from the problem perspective, we needed to be able to 3D print these parts because that's really the best option for construction that we had available to us. And it of course needs to be small scale because we can't be building entire tables inside of this small robot workspace. And speaking of the robot, we had several constraints relating to them as well. And namely, we have to have minimal motor torque because if we put too much torque on the servos, they'll end up faulting out, which we experienced firsthand. We had to use vertical output force because there was really no other way for us to put out force besides pushing things into the workspace floor. You need sequential construction because that's how a robot program works, as we have all learned now, or already knew, whatever. And when it came to the gripper design was parallel, and we also had a 3 centimeter maximum cross section. And then finally, we don't have vision with this robot implementation, so we needed to have staged parts that were going to be very consistent. All of that said, that all basically sums up to we had to design our stuff ourselves because nothing was going to fall into every single one of those constraints. And we ended up using Onshape to design these pieces. Generally, we have a large plate, a small plate, and legs, and that's what we use to construct everything available to us. And the small plate can be connected to the large plate in a couple of different orientations using some small friction-held pegs. The legs can connect into the bottom of both types of plates using this buckle type design. And then the legs also have a taper on the top of them so that we have some tolerance when we're trying to connect the legs. Otherwise, it would be more or less impossible to design in a quick fashion. Next slide. Yep. And then with all of our parts designed and printed, we printed them ourselves. We had to establish some assembly steps. And in this case, we designed them with the robot in mind using only vertical forces. And this is kind of like what you would see in a furniture like kit that you would buy, just a simple, few steps to assemble it, and we designed we wrote assembly steps for both the table and then also for the chair. But unfortunately, obviously, that you saw the video, we did not showcase assembling the chair. And John is going to talk about why that is, in addition to some of the other revisions that we had to implement before we could execute the program. Take it away, John.
Thank you, Jared. Well, as he mentioned, not everything went well according to plan at first, but after a few minor hiccups, we were able to fix these issues, hence why we are presenting these before you. Our first problem at hand with the table was, well, the construction of it. It just would not fit perfectly the first time around, like how everything is in life. It just doesn't work the first time around, right? And we just did that, and we had to sand them down, right? And we had to, as shown here, and here's a very short clip of us actually trying to sand it down.
So that they fit. This is quite sad. That would be great, wouldn't it? Like at the end of our presentation, just have a blooper reel of us.
Hilarious, yes, I know. The next course of action, was the tool frame, because the screws in the gripper just had to go. They were very inconsistent and would scratch our material, so that they had to be replaced by electric tape, which our lovely TA provided for us during that day in the lab. And as you can see, we just had to replace it here. However, speaking of tape, it served well for providing not only the thickness of it, but also for the playground as well. Our first plan of action was to design a cardboard cutout to strategically place specific parts in order to construct the table the way that we wanted to, without much hassle, worry, or worry from hitting the robot to the ground or crushing over the pieces. Unfortunately, one too many times from our experiences in the lab. And another purpose the tape has served has been also to mark the designated areas, as you can see in the right, where we would place our parts for the robot to work, for it to work in, the workspace for it to work in. And last but not least, just the timing of everything was just not in our favor. We had this bold vision, as Jared said, to show off our exquisite furniture builder by building a chair also. Unfortunately, due to the lack of time, or unfortunately due to like time constraints, we experienced, whether it was like individual schedules, printing problems, group malfunction, etc. We still got through to bring you folks this beautiful, delicate product and make do with the best that we have. And all of that process will be explained by our very own Desmond Doneen on the execution. Take it away, Desmond.
Awesome. Thank you, John. So when we started off this project, we wanted to make sure that we had the robot in mind when we were designing our parts and setting out our, as John called it, the playground. So in this diagram, you can see there's just a quick little overlay of how the pieces were laid out for the robot. The construction platform on the left is where those pieces were brought for construction. We had a row of leg pieces and the tabletop and the vanity mirror. The layout for all these pieces was extremely important because, as Jared mentioned earlier, there wasn't a vision function for this robot. So everything had to be precisely where it should be, and it had to be extremely repeatable as well. So one of the slides that John was talking about, we had our cardboard cut out and we had incisions all throughout it for each of the leg pieces, the tabletop and the vanity mirror, to sit in and be secure and be exactly where they needed to be while the program was running. So another step that we took towards making sure this project went successfully was that we had a very specific order of operations for our robot. As Jared mentioned, the only way that we could conceive to like stick pieces together was to like push them down with each other. These are like square pegs going into square holes. So we thought it'd be kind of ridiculous to try to do it any other way than just like stack them and push them down. So in this diagram here, you can see there's like a numbered order of operations, and this culminates in one of the 4 legs being put into the underside of the tabletop. If you see in a couple of the cube is representing where the tool is moving in the space. And some of the positions have duplicate numbers like 1 and 3, 4 and 6, and 10 and 12 are all duplicates. This is so that robot can have that perfectly linear up and down motion to place the parts. And we wanted to use linear moves also to keep the robot tool away from the parts as they were still staged to prevent the robot from accidentally knocking into other parts that it wasn't ready to interact with yet. Next slide, please. So after we had our playground set up and we had our plan of action kind of in our brains, we next thing that we wanted to do was teach the robot all the different points it had to go through. As I'm sure lots of you guys in your projects found out, this is very tedious to go point to point to point to point and right in the gripper moves and right in the opening of the gripper and all the different steps you have to take to place and construct something. So as you can see in this picture here, we're running the code that we taught to the robot. And we had 3 separate files for the code. We had one file that was the construction of the main table part, which is on the left. In that piece of code, there ended up being 51 discrete positions. And when we included the gripper moves, it was 73 lines of code. The middle panel you see there is the vanity mirror being added to the general table. And the final picture on the right is the surprise, the flip of, table flip at the very end. So next up we have Victor, and he's going to be talking to about various applications for this robot.
Okay, so first off, I want to talk about the benefits of using a robot for furniture applications. You probably hear this a lot, but robots can be used to replace humans. And in this case, it can be used to replace human assembly of furniture. This would allow for human labor to be reallocated and save money on at least this application. In place of the physical labor of assembly, though, more technical skills can be introduced, such as robot maintenance and programming. Using a robot would also result in minimal faults, which could come from human error. Because unlike humans, robots are more precise, and at least with proper maintenance, robots are very unlikely to make mistakes. And also robots are convenient since they are automated, because no one likes to do miscellaneous tasks. It can be grueling and annoying. Okay, next slide, please. All right, so typically when using a robot to construct objects, multiple robots are necessary, such as, like, for instance, one robot to hold a part and another one to fasten it. And when constructing different objects, typically each object needs like their own robot. Since we're using these robots with modular parts, a single robot can be used to construct any furniture, hence one robot for all. And so if we use less robots, we don't need to purchase and maintain as many robots for the same job, ultimately saving the company money. With less robots, there's also less space taken up. This goes hand in hand with saving costs, since smaller facilities will need to be built rather than larger. We could also use a display robot using them as long as we design the modular parts at conventions and demonstrations. All right. And as for potential features, if a vision system was to be applied to the robot, more features would be available, such as less staging would be required for the modules. With a vision system, a module can be picked up from any orientation and identified to fit the sequence. Currently, the modules are designed to easily assemble. However, if they can also be designed for a robot to disassemble. This would allow us to at least recycle and reuse modules for different models. And it could also introduce autonomously repairing the models. At the moment, the robot's only capable of assembling a chair and table, but more models can be designed to be constructed, such as dressers or beds. And that's all we have for you today. I would like to open the floor for any questions.
Good job, Group 9. Good demo, good presentation. All right, so before we open for questions, I do have a special inverse kinematic assignment for your group right after this.
I can't say I didn't expect it.
Okay. But I love the music in the demo video. Is that Swedish music or what?
I'm not really sure. Just some elevator music, to set the mood.
Curb your enthusiasm.
Oh yeah, that as well.
All right, let's open up for questions for Group 9.
I have one. Did you guys consider using magnets in the pegs to hold them together?
I mean, no, we didn't. But that would be a great idea. It was kind of like more so the simplicity of assembly with you just 3D print something and you're done kind of thing, rather than 3D printing having another step that requires adding a magnet in.
And that would be just too simple. They just stick and you just put it together.
Yeah,
this is more in line with what you would have in assembling real furniture.
In a way that actually would have made our project easier.
It would have made it much easier, but definitely less practical, because that's not, if you had like one of the constraints that we were considering was that we needed rigid connections. And although like a magnet might make it easier to connect them together, it would certainly make it less rigid.
Well, get a strong magnet. And don't let the robot near it, or it'll stick to the robot.
Never get it off.
So, other questions for the group?
First of all, props to you for 3D printing all these parts and designing all these parts. I know that's probably hard and took a lot of time. But
and money.
And money, of course.
Yeah.
But for us engineers, especially on the mechanical side, well, not mechanicals, but on the mechanical side, we seem to live in the CAD world, in a perfect world. And sometimes we seem to forget about like stack up tolerance or any tolerance when designing a part. And then you guys ran right into that by 3D printing a bunch of parts and having spent time to sand all the parts to the tolerance that you want, or to the design that you originally came up with. And then I think that's a problem that in the industry that we have is some people don't account for that. But my question to you is, what could you have done to avoid having spend time sanding all these edges, or I don't know if it's possible in the program that you use to do any analysis. And you're like, when 3D printing, you have like different temperatures, and then material might expand a little bit. So I don't know if that program has any options for that, and if it doesn't, what could you have done to predict those imperfections, or that error of 3D printing?
Yeah. So
sorry, that went on a lot longer than I thought.
So like I got you for sure. The main thing that we ended up running into is that we printed on 2 different printers. So when you're manufacturing parts from 2 different locations in particular, like you're going to have inconsistencies, and especially when it comes to 3D printers. Like I use my own personal 3D printer for printing all of the legs, and then we printed the main plates through the Maker Studio at like the Oakland Library. And so like I'm not sure what their settings were for their printer or anything like that, but it's definitely not going to be consistent with mine. And like even though I intentionally scaled my legs down by like I think it was like 2 or 3%, knowing that there was going to be some tolerance issues, because they were designed to be like perfect. So even though I scaled it down by a few percentage points, it still was the legs were too big. And there's definitely a lot of ways to account for that. And one of the ways that we ended up accounting for it is adding the intentional tolerancing angles to the legs, like tapering the legs rather than having them perfectly square. And I honestly just kind of absentmindedly forgot to add the taper onto like the friction held pegs. And so that's why those ended up being such a problem for like attaching the vanity onto the table. Those didn't have taper, and so it became much more vital to sand those parts down, even though they were printed on the same printer.
Yeah, but again, props to you for designing all that and 3D printing all that. So good job.
Thanks.
Yeah, so good questions. And well, this project is turning from robot to 3D printing.
It was a lot.
But I did mention maybe because of the restrictions, normally we have 3D printers in our maker club. So if you needed parts, we could have made it for you, but I did not know.
We didn't expect that we were going to.
That's
like we
okay.
had thought that I could just print them all on my printer, and then we were like, oh, this is going to take like about 60 hours of printing. So
Right. We are planning to have 3D printers in our industrial robotics lab, which will be operational just to make these small parts to attach to grippers and all that, because every student group ends up printing something to do something. And we encourage that. That kind of gets you into tool designing, like how if you have, you can, custom design something and try it out. So that's a good thing. Yeah, more questions for group 9. All right, so I have a question.
Yeah, shoot.
So as you pointed out in the presentation that we don't expect you to use vision with these projects. This is just introduction to robotics. It's way too much to expect that you're good in vision also. So you notice that everything needed to be extremely precise because you program it once and have to run it over and over again without any adjustment. Robot is very precise. Where you teach it, it will go there. But if the part is even slightly off, it's not gonna work, right? So fixtures, this is where fixtures come in. And I mean, you designed a fixture for your parts and it worked for you. And for industrial applications, those fixtures have to be extremely precise also. And they end up being very costly, when you are designing industrial applications. So that's the nature of how, if you have without vision, if you have to do pickup and application on the parts, it needs to be exactly where it's supposed to be. Okay, more questions for group 9? All right, so if you were using vision, how would you identify parts?
I feel like I need to apologize for my group mates because I'm stealing every question, but
No, they can join in.
Yeah.
Please.
I've worked with like a vision system before when I was in an internship in the past, and I know that in particular our parts would be, in a way, quite ideal for using vision because they have holes in very specific points on them and very like easily identified like edges because they're so square and things like that. So like identifying, say, like the corner of the piece, or like identifying the holes on the bottom of the plate when it's flipped upside down would be a really easy way to establish like a base frame or a frame based on the part, and then have the robot program to move in accordance to that frame rather than moving in accordance to just a universal frame.
Okay, so this is this operation when you're using vision is called the GPM, or geometric pattern matching. So if you teach a pattern and you're trying to find it, is there an easier way? Now you have a box full of parts. The robot opens the box. It's a IKEA robot, right? So it's gonna open the box and then take out the part and assemble it. So how the parts, when it looks at it, can we just have a marker, a barcode on it to identify so that it also knows how to assemble it? If it has a procedure for that assembling that furniture, there's a barcode on the box which tells the robot, what process am I going to use it? Maybe it's packaged in a certain way for robot assembly. So the parts are in a certain order. So when you open it, you have those QR codes maybe at a very precise location. And of course, you'll be using vision now because the robot has to go and see which part is where and exactly locate it and then operate on it. So yes, so you may have to design those packets for robot operation. But I have to tell you, any one of you assembled anything like a furniture with one hand? That's what this application was. One arm, one hand.
It was
there
hard.
wasn't a second hand. So you remember, so there is the complexity of that. What they did was they had to place it because you didn't have a second hand to hold things, right? So maybe a real furniture assembler may have a second arm also. to help out the other arm, and it will become much more easier to hold a part in one hand and assemble it using the other.
Yeah, we had even like gone through like one of the iterations of the leg that we were thinking was like a twisted lock mechanism rather than having the buckle lock. Was just like a push in. It's kind of like semicircles, 2 semicircles, and you twist and lock it in. And then we were like, well, we have no way to like hold the base in place, so it's not going to twist.
Exactly. So assembling with one hand is not an easy job. Anyway, all right, great job, Group 9.
Yes, thank you, everybody. Thanks for the questions.
Thanks so much.
Okay, we have the last group here, group number 10, Mario Builder Robot. Okay, guys, Nathaniel, take it away. Introduce yourself, demo, followed by presentation. Go ahead.
Okay. Okay, so hi there. We are Group 10, the Mario Builder Robot. My name is Nathaniel Austin.
I am Jacob Monks.
I am Nathan Bump.
And I think Brendan might be muted, but he is here. So without further ado, let's jump right into our robot demo.
You guys hear me now?
Yep.
Yeah, we can hear you.
Okay, good. Sorry about that.
Okay.
It's me, Mario!
Okay, so our initial idea for this, well, it wasn't our initial idea, but building this, we were trying to build an 8-bit sprite of Mario out of these different colored blocks, which originally we were going to put all of the individual blocks. That didn't go too well. So they were glued together. But so then the plan was to take these individual colored blocks and make a flush image where the blocks were as close together as we could get them. Which there are a couple spaces, more than a couple, but we got it pretty close. Next slide, please. So our initial idea, can you go back one, Nate?
Sorry, I think it went 2 for some reason.
Thank you. So our original idea was to make this creeper from Minecraft out of stamps, but we didn't do that because we were worried about the stamping motion of going back over and getting the same amount of ink every time, and then it drying out while we were the ink pad drying out while we were testing it. So then we transitioned into these painted blocks, and we changed into making a Mario sprite, which had more blocks. So we just made that change. So why was any of this project, I guess, applicable to the world? Because we were trying to minimize as much space as possible, right? If you're on a factory floor placing items, you don't want like 3 feet in between them if you can avoid it. You still need space, obviously, for the grippers to come down and grab things, but yes. So then very precise placement, or as precise as you can get it, and avoiding obstacles because you don't want your robot smacking into each other like it's a robot samurai fight. But then also using items of minimal variance, which Monks will talk about in a few seconds, because our items did not have a lot of variance, or they had a lot more variance than we would like. So obviously recognizing that is very important.
So as Nate sort of alluded to earlier, our first problem was that we had too many to work with. This had 2 results. One is that it would have taken 120, give or take, commands for all the movements, which would have been probably a 10-minute video that nobody wants to watch. And then the other problem that it created is that, excuse me, the other problem that it created is that every block was originally going to be screwed, and we actually screwed every individual block. That's why if you saw in the video, they all had holes in them. Well, we had to take them all out because when we decided not to do everything. And so the reason that the screws became a problem is that we were not aware of the gripper's width before screwing in the blocks. So if the gripper had to place each block individually, it would have had to move around all the screws, which just wouldn't really be doable given the gripper's width. And so then we decided to glue different blocks together to simplify the process, make it so that it didn't have to make as many movements. And then it would also allow it to more accurately or more practically maneuver through the different screws. And then if we go to the next slide, we talk about the second problem is that all of our materials that we used were not very good. The blocks we used were very cheap. Unfortunately, they were made of sawdust that was pounded down, I believe. And they were all not exactly the same size, which made it a problem when we were trying to make the image flush. So instead of trying to make it flush, we had to make it so that the robot had to place the blocks so that there were just tiny spaces between them for just enough wiggle room. Although in hindsight, what we could have done is maybe grab a flat piece of wood or some other thing with a flat wide end and just have it grab it and then slide the blocks next to each other. But that would have been way more movements, at least 4 or 5, if I remember correctly, extra movements per block, which would have extended it by another minute or 2, probably. And it also, I'm sorry, and then it also was the problem that the screws were not all perfectly straight because we screwed them all individually into the blocks by hand. So if the robot had to grab each one individually, and and we place the blocks differently every time because they all look the same to us, then the robot gripper wouldn't have been as good as it should have been because it's grabbing different screws of different heights each time that it does the program. And we want it to be reusable, so that didn't work out. So then Brennan will continue on the next slide.
So continuing on to figure out to get past these problems, first thing is we decided is to glue the blocks together. Not only does it make it easier to make the Mario image, but it saves a lot of time on the project itself. The other huge plus is that we could show much more motion with the robot. For example, we had a lot of rotation with the blocks. For example, if you look at the two images, we have the Mario image from left to right. We added rotation into that. And sometimes we had to reset the arm just to make sure that the wire on top didn't just get, pulled and yanked and ruined. But our basic simple outline for each block placement is start as a home position, move down, grab the black screw from the block, move vertically, move the placement point for the specific block, and if necessary, add rotation. Move down to ground, release gripper, move vertically, move to next block, and repeat the cycle. Can you move on to the next slide, please? One little thing is we also noticed with the grippers, originally we used a gripper with an indent to grab the screw, but we realized this indent was way too large with the stock one that we had at the lab room itself. So we decided to add a cushion into it, which is basically made of electrical tape. We also thought this would help with block placement as well, because if you're thinking that a flat press, once it releases, because it's very pneumatic, it's just instant, we thought they would be thrown, but they were not, obviously. But also came with that cushion is that the screws were actually getting stuck onto the cushion itself. So we then decided, let's just go with the two flat face grippers. And then once we did that, it was just smooth sailing from there.
Okay, so one of the problems we ran into initially was the block setup. So originally we tried using the grid lines on the FANUC workspace floor. But the problem is we couldn't get each block to be placed in the exact spot each time by us. So if it was just slightly off, the robot wouldn't be able to pick it up properly or place it properly. But Jacob was able to find a way to place the blocks the exact same each time. So for the Y direction, we used my cell phone as a spacer between the walls of the enclosure and the blocks to place. And then we used the bottom grid line and stacked up from there. So that way we were able to get the exact block placement every time so the program would run perfectly. So the end program has 143 commands. We used the gripper on-off program in order to actually program it. All of our movements are actually linear points, except for that one spot near the end of the video where you notice the robot going back to home. The reason we did that is because with linear movements, the robot does not care about the joint angle that the tool is facing, only the orientation of that tool with respect to the world frame. So we were having a problem where the wire was getting tangled in the rotation, but using a joint mode point fixed that problem. Next time, if we were to improve this project, we would definitely buy some better components because those blocks being off were not helping at all. We would also make sure that the screws are all at the exact same angle and height. We would make smoother movements for the robot to move, so that way the program would go quicker. And then we would also have a special frame to hold the blocks when picking them up, so we wouldn't have to devise that method of using the phone to set up the blocks each time. And then also, if you like, for added bonus, you could do vision tracking, so you could just have stacks of colored blocks for the robot to pick up and place as it sees fit. And that's about it. Do you have any questions for us?
Good job, Group 10. Good demo, good presentation. All right, we are open for questions for Group 10. Any questions? Okay, well, I have to mention that the robots in the lab, the speed is limited just for the safety of students, and these robots can fly. They can move very fast. So, but we have limits placed on all the speeds, so that way all the motion is safe, especially when students are learning about it. So that's one of the things about some of the demos which look like, oh my God, they are so slow. In reality, you're waiting for things to happen, but in reality, these robots in automatic mode can move very fast. Okay. All right. Questions, guys, for this group? Nobody likes Mario? What?
I was gonna ask, what's your favorite Mario game?
Oh,
The only one I ever played was Mario Galaxy.
ooh. Right now I'm playing all three. I got the remake for the Switch. It's pretty fun.
If I had to pick one, it would probably be Super Mario Galaxy, but I also have a soft spot for Super Mario 64 since that's the one I grew up with.
All right, let's come back to robots.
Yes.
You guys are taking the easy way out. We're not going to be asking questions about Mario games. But you mentioned that you initially you were thinking about doing a stamping or a painting. And then you thought that would be a difficult operation to do because of issues, and you went on a block place or pick and place. Can you guys tell me, what do you think that if you were doing a stamping operation or a painting operation or even a writing or drawing, what is one of the things which you need to make that a reliable, repeatable operation? Any one of you group members?
Well, one of the big things is that it definitely is like regarding the press of the initial ink. We would always have to make sure that the ink is at the same consistency level. And then once we get that placement down and then moving it onto the, let's say, the perpetual grid for that creeper, we'd also have to make sure that every single placement for that, let's say for every green and black color that it had, would be consistent. And for example, we also make sure that the gripper is grabbing the attached stamp every single time at the exact same position. Because if we don't grab it the exact same position, it'll come out at an angle and the image could come up wonky. It's a very, very precise thing that we were considering that with the tools that we currently have, we don't think we couldn't have gotten it done.
Okay.
Another thing was just wear and tear.
Right. Think about it this way. If you're picking a block, when you place it, do you actually make it touch the ground or release it just a bit above it?
No, we would need force control to keep
Yes.
that, to push against the ground.
You will need some kind of force control, force sensing, because you are applying pressure now. Another way to do it is what? If we don't have force sensing or force pressure, what would be another way to kind of bypass that?
If we could get a pad with like enough give on it to where when we push down,
Exactly.
there isn't like there are those really hard pads that if we were to push on it, it would just ruin the robot over time.
So compliance. So the tool compliance or part compliance is the other way you can compensate for that and do this kind of operations. If you don't have any of this, then you need force sensing, definitely. So yeah, those are more tricky applications where you have to do this stuff. Pick and place is usually the easiest for robots to do, precise picking, precise placement. Okay. Questions? Other questions for group 10? You did do an interesting move during the demo where you use the joint move to unwind. That's a pretty nice way to do it. As you are doing linear moves, yes, you could wind up the gripper depending on the sequence of moves, and doing a joint move, you can go to a precise position. So that was good. So I saw that. What would be an easier tool to handle here besides screws? I mean, if you had to do it and if you had luxury of everything what would be the easiest way to pick up blocks and place them? Which kind of tool would do it very precisely and very close together?
Probably the suction tool that you mentioned earlier. That way it could just precisely grab it right on the top.
Yeah, especially because if you have smooth surfaces on the top and you have a small suction tool, that would be really, because it will very reliably pick, and then you place it and release suction. And suction cups also have a little bit of compliance, so it gives you that also as you picking and placing. So
in a project where we had more high quality components, that absolutely would be a better option. But given that the size of the blocks were all different.
Yeah.
And also the fact that we originally were going to use the robot was just going to pick up the blocks and realize those are going to be way too small, or sorry, I lost my words here. We realized that the blocks, if we just went bigger, it would be just a big pain. So we went with smaller blocks to make it much more uniform image, stuff like that.
Right. All right. Okay, well, if there are no more questions, then group 10, great job. So that was very interesting set of demonstration, and I hope everybody learned some practical things which each one of these groups faced, and shared their experiences, the pros and cons of doing certain way. And hopefully this is very useful stuff which you can only learn hands-on doing applications using robots. I can't teach you in class unless you actually experience those things and try to solve them on them. All right, any last things anybody wants to share? We have a guest. If you want to share anything, this is the time. You can also comment.
Yeah, it was very impressive, and a lot of effort went into it, and it was a job really well done. So, congratulations to everyone.
Thank you, Imran. Yes. Do we have?
Yeah, it sounds nice job. I think.
Can you introduce yourself? I don't see your name, so I don't know who.
This is Joe Wyden from ABB.
Oh, okay.
Sorry.
No problem. No problem. We just wanted to know who this.
No, sure. So one of the themes I think tonight was it's the whole package, right? So a lot of you had talked about if you could do it differently, or with pieces not fitting together, and your robots are very precise, but it's a whole team effort where your engineers have to put your product and your components in the right places, so it's a pick and place every time, so your robot can be accurate, right? So it's your electrical engineers, your mechanical engineers have to work hard to get you as robot programmers to the right place so that you can finish the whole piece. And then second, I wanted to point out too is you also have to take into consideration that a lot of what I was selling tonight was like end product building and attachment to each other. And the one thing I think that, and I didn't hear mentioned too much, was you guys are touching with a robot like end pieces, which means you can't mark them, you can't scratch them, you have to be very careful with them. And so there has to be some delicate thought process in how your end of arm tools are going to touch this finished product and not ruin the quality of it for the customer. But again, nice job, great start, great way to think about it, but things for the future when you get more advanced.
Great comments, Joe. Thank you for sharing those. Anybody else? If not, guys, all of you did a great job. Now you guys can relax and enjoy the future presentations from the groups which are coming next Monday. Thank you, everyone. Have a great evening. We'll see you in the next presentation.
Thank you.
Thank you, everyone and guests.